Pluto is a distant and mysterious dwarf planet, once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon, or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the red flag of a possible hazardous collision between these two planets, which could be a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, angled 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacy of space mechanics. The three-body problem in space is about figuring out how three things in space, like Pluto, Neptune, and the Sun or Moon, move and affect each other with their gravity. Pluto's orbit is technically chaotic. Minor deviations in initial conditions lead to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos at bay. Recent computer tests have helped us understand how the big planets, like Neptune, Jupiter, and Saturn, affect Pluto's path around the Sun. Jupiter's gravity alone is strong enough to keep Pluto on a stable path for a really long time, even billions of years. These phenomena are essential in the context of the universe for maintaining the order and predictability of space's movement. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Pluto's orbit is a remarkable example of celestial mechanics at play, demonstrating both stability and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, showcase the intricate and dynamic nature of space. Predicting cosmic events, especially when it involves chaotic orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainty. While numerical simulations provide a powerful means to understand and anticipate the future paths of celestial bodies, they also highlight the limitations in our predictive capabilities. So why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune despite all these complex forces trying to keep such an event from happening? Neil deGrasse Tyson and Michio Kaku, both prominent figures in astrophysics, have expressed concerns about a potential collision between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a rare and catastrophic event in our solar system. The collision would release an immense amount of energy, likely shattering Pluto given its smaller size and icy composition. Debris from the collision could spread across the solar system, potentially creating hazards for other planets and their moons. For Neptune, such an impact could alter its atmosphere and potentially its orbit, depending on the specifics of the collision. Michio Kaku, a renowned theoretical physicist known for his work in string theory, brings a unique perspective to the debate as well. His views on the future of space exploration and the interplay between celestial mechanics and theoretical physics offer deep insights into the mysteries of space phenomena like Pluto's orbit. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto can provide crucial insights for future space missions. This knowledge can help in navigating the solar system more effectively, predicting potential hazards, and even in the planning of missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to explore other celestial bodies, offering a blueprint for how we might approach and understand distant worlds. When it comes to the physics of planets, celestial mechanics and theoretical physics are deeply related. The movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are connected to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astrophysics, offering a unique observational opportunity that could potentially relate to string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. The collision could produce extreme conditions of energy and gravity, potentially creating scenarios where effects predicted by string theory might become observable. For example, the high-energy impact could offer insights into the behavior of fundamental particles and forces under extreme conditions, a key interest area in string theory. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be profound, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's enigmatic dance around the Sun continues to captivate scientists and enthusiasts alike, offering a window into the complexities of celestial mechanics. While its classification as a dwarf planet sparked debate and redefined our understanding of planetary bodies, recent revelations about its orbit have reignited interest in its role within the solar system. Neil deGrasse Tyson and Michio Kaku, two prominent voices in astrophysics, have raised concerns about a potential collision between Pluto and Neptune, shedding light on the intricate dynamics at play in our cosmic neighborhood. Their warnings underscore the importance of understanding the gravitational interactions and orbital mechanics that govern celestial bodies' movements. Pluto's orbit, characterized by its eccentricity and steep inclination, defies conventional expectations and challenges our comprehension of planetary motion. Unlike the relatively circular orbits of its neighboring planets, Pluto's path traces a unique trajectory, intersecting with Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, particularly Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over millennia. Despite the chaotic nature of its trajectory, numerical simulations have revealed underlying patterns and mechanisms that help regulate its motion, preventing catastrophic collisions with neighboring celestial bodies. The three-body problem in space, involving Pluto, Neptune, and the Sun, epitomizes the intricate interplay of gravitational forces and orbital dynamics that govern the behavior of celestial objects. Understanding this complex system requires sophisticated mathematical models and computational simulations, which provide valuable insights into the long-term evolution of planetary orbits. Pluto's status as a dwarf planet has sparked debates about the criteria for planetary classification and the diversity of celestial bodies within the solar system. While its small size and distant orbit set it apart from the traditional definition of a planet, Pluto's significance as a celestial object continues to inspire scientific inquiry and public fascination. The study of Pluto's orbit extends beyond the confines of our solar system, offering insights into broader astrophysical phenomena and the fundamental laws of physics. The exploration of Pluto's orbit not only deepens our understanding of celestial mechanics but also offers a glimpse into the broader context of planetary dynamics within our solar system. Beyond its classification as a dwarf planet and the ongoing debate surrounding planetary definitions, Pluto serves as a critical case study in planetary formation and evolution. One of the enduring mysteries surrounding Pluto is its origin and composition. Believed to have formed billions of years ago during the early stages of the solar system's formation, Pluto's composition is predominantly icy, with a mixture of rock and water ice. Its surface features, including vast plains of frozen nitrogen and methane, suggest a dynamic geological history influenced by external forces such as impacts and internal processes like cryovolcanism. The discovery of Pluto in 1930 by Clyde Tombaugh marked a significant milestone in astronomy, expanding our understanding of the outer reaches of the solar system. Initially classified as the ninth planet, Pluto's status underwent revision in 2006 when the International Astronomical Union redefined the criteria for what constitutes a planet. This decision, which reclassified Pluto as a dwarf planet, sparked considerable debate within the scientific community and among the general public. Despite its reclassification, Pluto continues to captivate astronomers and planetary scientists due to its unique characteristics and orbital dynamics. Unlike the 8 major planets that orbit the Sun in relatively circular paths aligned closely with the ecliptic plane, Pluto's orbit is highly elliptical and inclined at an angle of approximately 17 degrees to the ecliptic. This orbital inclination contributes to Pluto's distinctive orbital path, which intersects with that of Neptune, albeit without resulting in collisions due to gravitational influences from other celestial bodies. The study of Pluto's orbit raises intriguing questions about the stability of planetary orbits and the long-term dynamics of the solar system. Numerical simulations and theoretical models play a crucial role in predicting the future paths of celestial bodies and understanding the complex interactions between planets. These simulations indicate that while Pluto's orbit is chaotic over millions of years, it remains dynamically stable within the broader framework of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as suggested by astrophysicists Neil deGrasse Tyson and Michio Kaku, highlights the ongoing uncertainties and complexities in planetary dynamics. While such an event remains hypothetical and highly improbable in the near term, the gravitational dance between Pluto and Neptune underscores the intricate balance of forces that govern the celestial bodies within our solar neighborhood. Beyond its scientific significance, Pluto's exploration offers practical insights for future space exploration missions. The New Horizons spacecraft, launched by NASA in 2006, provided unprecedented images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed stunning details of Pluto's surface features, including mountains of water ice and vast plains of frozen nitrogen, enhancing our understanding of the geological processes shaping the distant dwarf planet.